Hey everyone, this is Joy, and I will be teaching you all about the Pearson's product moment correlation. It is referred to as Pearson's correlation or simply as the correlation coefficient. This is very helpful if you want to compare the two variables if they both have a correlation or relationship. Remember that it shows a linear relationship. If the relationship between the variables is not linear, then the correlation coefficient does not adequately represent the strength of the relationship between the variables. Here we have Carl Pearson, the man who founded the statistical idea. He is a British statistician, leading founder of the modern field of statistics, prominent proponent of eugenics, an influential interpreter of the philosophy and social role of science. He has been credited with establishing the discipline of mathematical statistics. As what I have said before, PPMC is a measure of the strength of a linear association between two variables and is denoted by R. These are used in statistics to measure how strong a relationship is between two variables. As you can see on the picture on the right, it shows a scatter plot between the average price and production. A scatter plot is a type of plot or mathematical diagram using Cartesian coordinates to display values for typically two variables for a set of data. The symbol for Pearson's correlation is P when it is measured in the population, and R when it is measured in a sample. Because we will be dealing almost exclusively with samples, we will use R to represent Pearson's correlation unless otherwise noted. Pearson's R can range from -1 to 1. These are the degrees of correlation. Positive -1 indicates perfect correlation. Positive -0.75 to positive -0.99 indicates high correlation. Positive -0.51 to positive -0.74 indicates moderately high correlation. Positive -0.31 to positive -0.50 indicates moderately low correlation. Positive -0.01 to positive -0.30 indicates low correlation. 0 indicates no correlation. There are three things we have to remember about a Pearson's R. First, if your R is positive, then it indicates a positive correlation. It means that for every positive increase in one variable, there is a positive increase of a fixed position in the other. For example, shoe sizes go up in almost perfect correlation with foot length. I provided some other examples about this, so just pause the video. A negative correlation means that for every positive increase in one variable, there is a negative decrease of a fixed position in the other. For example, the amount of gas in a tank decreases in almost perfect correlation with speed. No correlation means that for every increase, there isn't a positive or negative increase. The two just aren't related.
Now let's take a look at example 1. In example 1, we're looking for the correlation between people's age and glucose level. Firstly, what we need to do is add 3 more columns. Now, how do we get these columns? Well, for the first additional column, you simply multiply your first and second column, ignoring the subject column, as that is just a column counting how many variables are in the columns. So we multiply age, our x, and glucose level, our y, to get the xy column. And then for the last 2 columns, namely x squared and y squared, we simply just square all of the variables in the x column and then square all of the variables in the y column. Now once we've added the 3 additional columns, we sum up all the columns, getting the summation of the x column, y column, and so on and so forth. And once we've gotten all of that, we can finally use the formula. So R is equal to n, or the population, times the summation of xy minus the summation of x times the summation of y over the square root of n times the summation of x squared minus the summation of x quantity squared multiplied by n, or the population. times the summation of y squared minus the summation of y quantity squared, wherein n is equal to the number of variables in the column and r stands for our sample. Seems like a difficult formula, but it's actually quite easy. So we substitute the variables, input that into our calculator, and we get 0.53. And if we recall what we discussed previously, we know that our answer falls under moderately high correlation.
Let's proceed in formulating the null and alternative hypothesis. The difference between the two is that the null hypothesis reflects that there will be no observed effect in our experiment. This hypothesis is denoted by HO, while the alternative or experimental hypothesis reflects that there will be an observed effect for our experiment. This hypothesis is denoted by HA. For our example, our null hypothesis is there is no significant correlation between age and glucose level, while our alternative hypothesis is there is a significant correlation between age and glucose level. We will use the 5% level of significance. The significance level, also denoted as alpha, is the probability of rejecting the null hypothesis when it is true. Moving on, degrees of freedom is the number of independent pieces of information that went into calculating the estimate. To solve this, population or n minus 2, our n is 6, and you will subtract it with 2. Therefore, our degrees of freedom is 4. Our tabular value is 0.811. To find the tabular value, base it from your degrees of freedom and the level of significance. We are using two-tailed, by the way. The intersection of DF and the 5% level of significance would be your tabular value. You could get the table of tabular values in the internet. Let's now formulate our decision. Remember that if the computed value is lesser than the tabular value, accept the null hypothesis. If the computed value is greater than the tabular value, then reject the null hypothesis. If you are wondering where we get the computed value, it is actually the R itself. From our example, we can observe that the computed value, or the R, is lesser than the tabular value. Hence, the null hypothesis is accepted. There is no significant correlation between age and glucose level.
Now let's proceed to example 2. This time we're looking for the correlation between math and science. So here we just repeat what we did with example 1. We add the 3 columns, the x, y column from multiplying our x and y columns with each other, the x squared column from squaring the x column, and finally the y squared column from squaring the y column.
So now, let's get the summations. Summation of x is 141. Summation of y is 118. Summation of xy is 1794. Summation of x squared is 2119. And summation of y squared is 1528. Use the formula and then substitute. After substituting, input it in the calculator and you will get 0.98, which falls under high correlation. Our null hypothesis would be there is no significant correlation between math and science, while our alternative hypothesis would be there is a significant correlation between math and science. Use the 5% level of significance. Afterwards, solve for the DF. Our DF would be 8 since we subtract 10 with 2. Our tabular value would be 0.632. Now, you are ready to formulate a decision. Based from what we solved, our computed value is higher or greater than the tabular value. Hence, the null hypothesis is rejected. There is a significant correlation between math and science.
For this third example, let's see if you can solve it. You can pause the video to give yourself some time. Okay, so I presume you've solved it, so let's see if your answer was right. We create the 3 columns, get the summations, substitute using the formula, and we get 0.72, moderately high correlation. Were you right? If not, it's okay, just practice and you'll get it.